Okay, welcome to the second session of the afternoon talk. Here we are very happy to have Yui Hayashi here to talk about non-invertible symmetry of Cardy-Rabinovici model and the mixed gravitational anomaly.
Thank you for the introduction. I'm Yui Hayashi from Yukawa Institute, Kyoto University. Well, first of all, I'd like to thank the organizers for giving me this chance, giving me this opportunity to talk here. I'm talking about non-invertible symmetries in Cardy-Rabinovici model, which is a toy model for SUN Yamil's theory with theta term. And this work is in collaboration with Yui Tanizaki, who gave a talk about solitonic symmetry. Doesn't work. I see. Okay, here is an overview of my talk. The model we study is the Cardy-Rabinovici model, which is a toy model for vacuum structure of SUN Yamil theory with topological theta angle. And I will discuss non-invertible symmetries and its sort of anomaly in this model. And the story is as follows. First, we find that a sort of duality in this Cardy-Rabinovici model can be understood as dualities between the Cardy-Rabinovici model and its ZN1 form gauged model. I mean, the Cardy-Rabinovici model has a duality with ZN1 form gauging. So from this type of dualities at the self-dual parameters, we can construct non-invertible symmetries by recently popular half-space gauging technique. And finally, we find a mixed gravitational anomaly of this symmetry for some cases, which severely constrain low energy dynamics. For example, it can rule out the trivially gapped vacuum. And actually, the conjectured phase diagram obtained in old literature is consistent with this new strong constraint. Okay, let me start with what you are familiar with, the half-space gauging construction. The half-space gauging construction of non-invertible symmetry is nowadays a popular way to construct non-invertible symmetry, which is applicable to higher dimensional theories. The main idea is a generalization of Kramers-Wanier duality defect. Okay, as you know, the Kramers-Wanier duality defect is non-invertible symmetry in the criticalizing model. And in the criticalizing model, the Kramers-Wanier self-duality can be written as invariance under Z2 spin flipping gauging. And when the theory is invariant under the gauging of discrete symmetry, then we can define non-invertible defect by the half-space gauging setup, right? And from this viewpoint, we can easily generalize to higher dimension. And for example, for some four-dimensional quantum field theory can be invariant under gauging of ZN1 form symmetry. And when theory is invariant under ZN1 form symmetry gauging, then just as in Kramers-Wanier duality defect, we can define non-invertible symmetry, codimension 1 non-invertible symmetry defect by half-spacing ZN1 form gauging. And this construction opened up a broad class of, a broad class of non-invertible symmetries in higher dimensional theories. So we would like to explore physical applications to four-dimensional gauge theories. So with this motivation, we focused on the Cardy-Rabinovici models. Let me briefly introduce what is Cardy-Rabinovici model and why is it interesting. Okay, our physical motivation is in quark confinement and its topological nature. A popular understanding of quark confinement is a real superconductor picture. And in this scenario, we expect magnetic monopole condenses in vacuum. Then by dual Meissner effect, quarks and anti-quarks feel a confining force due to due to the condensation of the magnetic monopole. And this picture tells us a lot about topological nature of vacuum structure. So by the Witten effect, the monopole acquires electric charge theta over 2 pi by increasing theta. So at theta equals 0, as I said, we expect monopole condense. But by the Witten effect, at theta equals 2 pi, we expect electric charge minus 1 dion would condense. Then we would have this type of multi-branch structure, which can be indeed guessed from the large N argument. And when N is not so large, there could be an exotic diode condensation phase as an intermediate phase, known as oblique confinement phase, proposed an interesting possibility proposed by Toft. So such a structure will give us valuable insight into confining vacuum structure. So we would like to study this kind of things. And Cardy and Rabinovici propose a simple toy model for this purpose, which we will call Cardy-Rabinovici model. Originally, Cardy-Rabinovici model is formulated as a lattice gauge theory, but let me introduce only continuum essentials. Essentially, the Cardy-Rabinovici model is four-dimensional U1 gauge theory with charge n electric matter and charge 1 magnetic matter. And charge n electric matter is introduced as charge n Higgs field in a naive low energy limit, and the magnetic monopole is actually introduced as a violation of Bianchi identity on the lattice scale. And since we have introduced only charge n electric matter, this theory has GN1 form symmetry, mimicking the GN1 form center symmetry in the SUN-Yamil theory. And the partition function of the Cardy-Rabinovici model can be symbolically, it's actually defined on lattice, but we can symbolically write its partition function as this equation. And well, in addition to the U1 gauge sector, the matter part consists of all possible insertions of electric charge n line and magnetic charge 1 line. And here we introduce unconventional n factor here for 2 pi periodicity of theta, because in this model, there is explicit magnetic line here. So by the Witten effect, if we shift theta by 2 pi, this magnetic line acquires charge 1 electric line. So yeah, usual theta periodicity doesn't work, but if we shift theta by 2 pi n in usual convention, then this Toft line acquires charge n electric line, and this extra charge n electric line can be absorbed by the path integral over the Higgs field. I mean, the sum over the electric line. So by introducing theta, by introducing n here, the theta becomes 2 pi periodic in this theory. Okay, here is a conjugated phase diagram by energy versus entropy argument for matter line operator obtained by Cardy and Rabinovici. This is a phase diagram when there is always some condensation. I mean, this is a gapped scenario. Where the vertical axis is the inverse coupling and horizontal axis is theta. And when the coupling is weak, we have electric condensation. So we have Higgs phase here. And when the coupling is strong, then the magnetic condensation wins, and we have monopole condensed confinement phase. And if we shift theta by 2, if we increase theta, then the monopole condenser confinement phase becomes dion condenser confinement phase. And at stronger coupling, there could be more exotic condensation, more exotic dion condensation as an intermediate phase. And if we fix coupling strong value, then this theta dependence mimics the theta dependence of SUN Yang theory. So this gives an interesting playground to study vacuum structure of strong interaction with theta term. And a remarkable point of this phase diagram is the apparent SL2Z invariance generated by electromagnetic duality and shift of theta term. The S transformation is an inversion of complex coupling. At the same time, we interchange the electric charge in the unit of N and magnetic charge. And the T transformation is just describe the Witten effect. So by T transformation, the monopole condenser confinement phase becomes dion condenser confinement phase. So yeah, in some sense, this phase diagram has kind of electromagnetic duality and T duality. But what they are, I mean, the usual S transformation in the Maxwell theory doesn't work here. So the standard S transformation is not a duality of Cardy-Rabinovici model, because the Cardy-Rabinovici model has electric charge N particle and magnetic charge 1 particle, and standard S transformation by the standard S transformation, the S transformed model has electric charge 1 and magnetic charge N matters, so they are different. But here we notice that the S transformed model has GN1 form, magnetic GN1 form symmetry instead of electric GN1 form symmetry. So here we can guess that this S duality is actually a duality between Cardy-Rabinovici model and its GN1 formed gauge model. And it turns out that this guess is true. Okay, next let me move on to the result section. Here I introduce notation. I assume that I restrict ourselves to this environment, and yeah, this is a reminder of partition function. And yeah, when we gauge GN1 form symmetry, we can attach this discrete theta term. And we write the label of discrete theta term by this subscript. Okay, so as a warm-up example, let me talk about S defect in the Cardy-Rabinovici model. The S transformation on the phase diagram, S transformation is an inversion of complex coupling. And the fixed point is tau equal I. And at this fixed point, we expect some kind of self-duality. And this S self-duality at tau equal I can be realized as this type of this invariance under the GN1 form gauging. Let me explain a bit. Well, the right-hand side is the original Cardy-Rabinovici model at tau equal I, which is the U1 gauge theory with electric charge N matter and magnetic charge N1 matter. And the left-hand side is a GN1 formed gauge model. And actually, the GN1 form gauging results only in the scale of U1 gauge field by N. I mean, we can combine the original U1 gauge field and GN1 form gauge field into a new U1 gauge field. And by this rescaling, the charge N electric line becomes charge 1 electric line. and charge 1 magnetic line becomes charge n electric line. Sorry, charge n magnetic line. So the left-hand side can be represented as U1 gauge theory with charge 1 electric matter and charge n magnetic matter at this coupling. And these theories can be connected by the standard electromagnetic S transformation. So we have at tau equal I, we have the invariance under the gauging. And because of this, we can construct non-invertible defects by half-space gauging following this fusion rules. So the fusion of this duality defect gives charge conjugation defect and condensation defect. Here, eta is a GN1 form defect. And on the other hand, we can use this non-invertible defect, this non-invertible symmetry to constrain the low energy dynamics. And for some n, we can rule out trivially gapped phase. And together with CP symmetry, we can rule out the trivially gapped phase for n is larger than 2. And let me discuss a more non-trivial example. Priority defect, ST inverse defect. On the phase diagram, in terms of the complex coupling, the ST inverse transformation can be written as here, as this transformation, and the fixed point is here. And this transformation interchanges between Higgs phase and monopole condenser confinement phase and dion condenser confinement phase. And an important point is that this T inverse transformation can be taken into account by attaching discrete theta term. So the ST inverse self-duality at fixed point here can be realized as this type of invariance under the gauging. So on the left-hand side theory, as before, we can combine the original U1 gauge field and the N1 form gauge field into a new U1 gauge field. But in this procedure, the discrete theta term for the N1 form gauging becomes 2 pi shift of the original theta term in the Cardy-Rabinovici model. So the left-hand side theory becomes U1 gauge theory with electric charge 1 matter and magnetic charge n matter at this shifted coupling. So T inverse transformation can be taken into account by this attaching discrete theta term. And this theory and these theories can be connected by the standard S transformation as before. So we have this type of invariance under the GN1 form gauging. And from this property, we can construct non-invertible defect by half-spacing gauging and reflecting that the ST inverse is triarity, not the usual fusion, but the triple fusion gives the charge conjugation defect and the condensation defect. The usual fusion gives charge conjugation defect and the orientation reversal of triarity defect. And an interesting point here is a mixed gravitational anomaly. In terms of the partition function, this relation has been written as this equation. And this factor can be derived but can be derived by similar calculation, just as the Witten's calculation of S transformation in the Maxwell theory. And yeah, the interesting point is this signature dependent, sigma is the signature of the spacetime manifold, and the interesting point is this signature dependent phase factor. And following the ST inverse and following the ST inverse mixed gravitational anomaly in the Maxwell theory, we call it mixed gravitational anomaly of this non-invertible symmetry. And yeah, this factor can be non-trivial if we put, for example, on a K3 surface. On the K3 surface, sigma is -16, so this becomes non-trivial. And yeah, and then we can rule out trivially gapped phase or any symmetric TQFT, but because yeah, this non-trivial phase cannot be reproduced by such partition function. So for example, we can rule out trivially gapped phase because any SPT partition function cannot reproduce this non-trivial signature dependent factor. So this mixed gravitational anomaly severely constrains the low energy dynamics. Okay, so what are possible scenarios? Well, of course, free photon Maxwell theory can match this anomaly, but what about gapped scenario? Well, interestingly, the conjectured phase diagram obtained by Cardy-Rabinovici is consistent. This gapped version of the conjectured phase diagram is consistent with the anomaly constraint. So we can satisfy this anomaly relation by superposing Higgs phase and monopole condenser confinement phase and dion condenser confinement phase. Oh, thank you. And yeah, and we can continue this type of analysis. So we can find the invariance under the gauging and construct non-invertible symmetries and constrain low energy dynamics at any ST inverse, any SL2G invariant fixed point. For example, here or here. Okay, here is a summary. So I have talked about non-invertible symmetries in the Cardy-Rabinovici model, which is a toy model for vacuum structure of strong interaction with topological theta angle. And yeah, at the self-DL point, at the self-DL parameters, we can construct non-invertible symmetries. And for some cases, we find mixed gravitational anomaly, and this gives non-trivial constraint on low energy dynamics or RG flow. Thank you very much.
Come to the last talk of this afternoon session. We have like Daniel Brennan to have the anomaly of the discrete one-form symmetries in QCD-like series.
Oh, okay, it's working. Cool. All right. Yes. So thank you again very much to the organizers, both for organizing this conference and for inviting me to talk. Yeah, so I'm going to be the first person to talk on the board. It's going to be sort of a semi-technical talk, so I'm going to try to blow through most of the details. And because I know this is the last talk of the day as well, and we all want to get to the reception. So, right, so this is going to be based on some upcoming work with Ken and Trilligator. And yeah, so I would like to also advertise that Ken is going to give a much more in-detailed talk about this project in the next week. So if you would like more details, please feel free to ask, but you can also ask Ken next week. Okay, so today I'm going to talk about discrete anomalies of one-form symmetries in QCD. And in particular, that means we're going to be working in 4 dimensions. And as we all know now, global symmetries are the sort of fall under this sort of categorical structure. But today I'm just going to be talking about group-like theories. And so in particular, I just mean higher form symmetries, one-form symmetries and stuff like this. And very good. So I feel like I don't need to give very much introduction because of all of the talks we've already had today. But so today we're really going to be talking about discrete higher form symmetries, and in particular one-form symmetries. So as we all know, you can think about a gauge theory has a center symmetry. So it's some sort of one-form center symmetry. What this means is that you have topologically protected line operators in your theory. And so one form. And of course, we know from all of our collective work on generalized symmetries, that even in the case of discrete gauge theories, or even in the case of discrete global symmetries, we know how to turn on background gauge fields. And so today we're going to be studying anomalies. And so I would like to, I guess, reiterate that the definition of anomaly I will be using is that essentially a non-invariance of the partition function under background gauge transformations. Some sort of anomaly. Of our background gauge fields. So good, so this phase here is what we often call the anomaly polynomial, or rather the inflow of the anomaly polynomial. And yeah, so this is sort of our basic setup. And so today we're really going to be talking about how you can compute these anomalies. And so I'd like to differentiate between 2 different techniques, or 2 different classes of anomalies. There are sort of perturbative anomalies, and then there's non-perturbative anomalies. And perturbative anomalies are sort of contain all of the classic ones we know. They're sort of defined by the fact that you can measure them with local correlation functions. So the classic examples of this in 4 dimensions is if you have a bunch of 0-form symmetries, you can compute the 3-point function. Just mute first. Of currents. And you'll find that this is proportional to a contact term. Yeah. A contact term whose coefficient is fixed and describes the anomaly. So this is, of course, a very classic example of just 0-form symmetries. But you can also measure perturbative anomalies of higher form symmetries. Like, for example, in just U1 Maxwell theory, there's a mixed anomaly between the 1-form electric and 1-form magnetic symmetry. And if you measure the 2-point function, the field strength, again, using just the equations of motion, you find this is proportional to a contact term whose coefficient, well, usually 1, it describes the anomaly. So this contains most of the anomalies that we know how to compute and give us a lot of constraints on RG flows in quantum field theories. So we're going to be talking about non-perturbative anomalies, which cannot be measured by local correlation functions. And so there's two nice examples of these. The first is the Witten anomaly. And this arises in, for example, when you have an SU2 symmetry, either gauged or global. And the Witten anomaly occurs when you have an odd number of fermions that transform in the spin 1/2 representation. And one way to, okay, I don't want to get too far ahead, but this is essentially what you can show is that there is an element of pi4 that maps into SU2. So there's a winding configuration you can construct so that a partition function will be anomalous under this action. And there's another non-perturbative anomaly, which is this sort of called the new SU2 anomaly. And this is a shear gravitational anomaly. So, and so, yes, this is another type of anomaly. And both of these can be measured by some sort of index theorem. So, and in general, actually, I believe actually, so for example, these anomalies can also be measured by index theorems. And that's sort of a unifying idea of how you can compute anomalies. So ours is also going to fall under this sort of non-perturbative class. And what we're going to consider is in a theory with some sort of Z2 one-form symmetry, which has some sort of background gauge field, we'll call it B2. And then you can have anomalies which are of the form W2, I guess B2. And so we're also going to show that there's an index theorem that controls this. And the way that these are all derived, sorry. So the way that these are all derived sort of stem from actually this original idea of the perturbative anomaly. So, right, as I said, you can measure it using local correlation functions, but another way you can measure it is by looking at the instanton measure of the path integral in the presence of an instanton. So in general, when you have some sort of instanton background, the partition function, say with some sort of fixed background gauge field, sort of has a nice split. So you have a path integral over all the fermion modes, and this usually includes some sort of odd number, well, an uneven number of psi's and psi bars, and that's determined by an index theorem. So I'll just say these are d psi zeros. So these are the fermion zero modes. And all of these anomalies can be captured by the fact that this part of the fermion measure transforms anomalously. So sort of the logic is that you pick some background, and then you look at the variation. So 1, 2, and then you look at variation of this d psi 0. Okay. Cool. So in the theories we're going to be talking about, we're going to be taking 4D QCD theories. So what I mean by this is some sort of G gauge theory, plus some sort of fermions in some representation R of G gauge. Actually, yeah. So in general, you can couple this theory to background, or these fermions only see a sort of subclass of the full gauge bundle. So you can say that they transform under some sort of total bundle faithfully. So we have some sort of G gauge here. And depending on the representation, it might not actually see all of the gauge groups. So here gamma is a subset of the center and corresponds to a one-form symmetry. And I'm also going to make a simplifying assumption here, actually. So we're also going to say that there's some number of fermions, and they transform under some global symmetry, which I'm just going to call F for flavor. And they also transform as spinors in spacetime. So our analysis, I guess you can just say here, we're going to be able to put this theory on spin manifolds. And so what that means is we need to consider some sort of spin structure. And so what I'm going to be considering is the sort of general case where you have a Z2 quotient here. And what this does, it allows for a spin GF structure, which means that you can go onto non-spin manifolds if you, in addition, turn on a discrete flux in GF. That's correlated. And Z2. Okay. And so the background we're going to be considering is the case where we turn on a Z2 flux inside of gamma, and we go to a non-spin manifold. Background. So, and I'm actually going to pick a particularly nice non-spin manifold. I'm going to pick CP2. So CP2, and then you have plus some sort of, I call it W. Sorry, I'm going to use B2 with a B2, which is again, it's a Z2, the Z2 gauge field that sort of turns on a Z2 subgroup of gamma. And CP2 is especially nice because when you turn on some background flux, essentially the point is that there's a single H2 class in CP2, and if you turn on a flux in that, it's automatically an instanton. So what you have now is some sort of fractional instanton. Okay, so now what that means is that this flux background just automatically has some collection of fermion zero modes. And so now what we need to do is just find some variation or some action on our theory under which the fermion measure transforms non-trivially. These are like all broken. Okay. Good. So this symmetry that we're going, or this action that we're going to construct is actually a little bit non-trivial. But thankfully, smarter people than me, like Edward Witten and collaborators, sort of figured this out for us, or a version of it at least, a subset. So the CP2 is nice because there's an involution called, essentially there's a complex conjugation action on CP2. But what you can show is that this is actually the same thing as a pi rotation along some axis. And what this does is it actually takes our flux and maps it to minus itself. So here we have some B2 maps to minus B2. And we also have our discrete flux of the flavor symmetry maps to minus itself. Now, of course, these are Z2 gauge fields, so we have not changed the topological class of them at all, but we have changed the literal flux background because in our quantum field theory, we're dealing with continuous fields. So you actually, when you turn on a background, you have to pick a lift, or a representative rather, which is a specific instantiation of G gauge and G flavor. So, so this by itself is not a symmetry, but what you can show is that in many cases, there actually exists an interior element of G gauge or G flavor that can undo this transformation. So I'm going to call it capital W. And a nice way you can construct such a map is you can imagine that these Z2 fluxes are the Z2 flux of some SO3, which of course is equal to SU2 mod Z2, that's embedded into, call it G or F, that's embedded into G sub G or G sub F, depending on your theory. So in this case, you can embed B2 and W2 along the carton of your SU2, and then there's actually the vial element maps the T3 to minus itself, and that is how you can construct this map that undoes the symmetry. So what you find is that there's sort of some total symmetry, which is complex conjugation composed with this interior element of the two groups. And this leaves your bosonic background invariant. So this is a classical symmetry of your theory in this background. So now what we can do is try to figure out how this acts on the fermion measure. And so as it turns out, right, so good. So here we picked some embedding of some Z2 inside of our gauge group and our flavor symmetry group, but we'll just talk about the gauge group. So this is sort of the Z2 that lies inside of some U1 subgroup of G gauge. And so this U1 subgroup, which I'll call U1 sub G, is acted on by charge conjugation under this. Sorry. And as a group, this is just given by O2. So what this means is that actually the space of fermion's zero mode solutions transform under the transformation under the group O2. And you can show that you only have fermion zero modes if they have non-trivial charge under U1G. And so what that means is that phi hat on each all the fermion zero modes transform in two-dimensional representations in which phi hat is this matrix. So now I can tell you exactly how this acts. So you would say if there are, so I'm going to call this my index, whatever this letter is, maybe I. So if you have this many total fermions, that means you have I over 2 representations, and then the fermion measure transforms as the determinant of this matrix to this power. So transforms as -1, the index over 2. Good, so now we've constructed some flux background. There's some action under which the fermion partition function transforms as a phase. So we have an anomaly. And I can tell you that this anomaly is exactly the one that I promised you. W2, dB2. Okay, so cool. So now we know how to compute all of these. And so the important part is now I've literally just reduced this entire anomaly to computing an index. We can literally call this this coefficient as sigma, which is just the index over 2 mod 2. Yes.
How can you distinguish with this method, like an anomaly, this one from like a W2 cap W3, since both are both the fields are flipped by the conjugation, the automorphism of CP2?
That's right.
You're gauge transforming everything, no?
Good. So indeed, you can this anomaly. You can actually compute these two anomalies separately, and you can just show that. Yeah. So you can turn on an anomalous phase. As you said, that's a W2 of the tangent manifold coupled W3, and essentially you could just compute them separately. Yeah, exactly. Okay, so now I just, since I'm running out of time, I just wanted to show you guys some cool examples and applications. Before our paper, which has not come out yet, the sort of state of the art was that you have to use symmetry fractionalization to compute these anomalies. And the way you would do that is by looking at the space of fermion zero modes in the presence of a magnetic monopole, and then quantizing it and determining the representation under the global symmetries, which is a bit of a hassle. So this way is much quicker. I just give you some flux background and then you compute an index. Cool. And so this is a much more efficient way of computing all of these anomalies. And so I will just give you a sort of small table of sort of new anomalies. And so, for example, if you take SU2 gauge theory, there's a new anomaly, or you can show that there's an anomaly when the fermions transform under the spin representation of when the spin is 1 or 2 mod 4. And I'm also taking NF, which is 2 times little NF copies of the representation. So you find that there's this, there's an anomaly, which is, I'm using this notation. The anomaly is dependent on the number, but you find that there's this new case, which is the spin 2 case with 2 fermions, 2 fermions in the spin 2. This is some new anomaly that's not been computed before, and it is it's the only new case for SU2 that is asymptotically free. And you can also do the same thing for SU NC. I'm just going to write down the ones that are non-trivial. So if you're in the adjoint representation and you find this dependence, find that for all spin NC fermions in the vector representation, that there's this anomaly for odd little NF, and that you find for spin 2 NC odd. In the adjoint representation, again, new anomalies. So the anomaly of SU2 with a single fermion in the spin 1, or rather SU2 with 2 fermions in the adjoint, has been known for a while. This was discovered by Donaldson and Witten, or well, Donaldson, Witten, in computing the path integral of n equals to SU2 gauge theory. But now we've been, and there it was sort of related to an anomaly of picking an orientation of instanton moduli space to define the path integral. But here we've been able to compute it for all of these groups, and you can also do it for, I mean, you can do this for all gauge groups, and you find that there's this whole family of solutions. Okay. In my 5 remaining minutes, I'm going to try to tell you about another cool application, and that's the idea of symmetric mass generation. So the idea of symmetric mass generation, at least in the setting of QCD, is that there exists chiral gauge theories, which by that I mean that there's no mass term. And there exist chiral gauge theories such that so that all of their symmetries are non-anomalous. And so the question is, does there exist some operator that you can deform the theory by so that it flows to the trivially gapped phase? Good. So there's a nice family of examples that seem to have this property, but I would like to show you now that some of these theories actually have this new non-perturbative anomaly. And so we can sort of rule out are G flows of a particular proposal. So, yes. The standard model is a chiral gauge theory, but it has anomalous symmetries.
But I mean, for using the Higgs mechanism, you give mass to fermions. No?
I think actually, I thought the claim actually was that the Higgs mechanism doesn't give masses to everything.
Oh, okay, I see. So this is a case in which you can really gap the full theory.
Yes, you got the full
Okay,
theory.
okay.
Sorry. Yeah. Good. So the class of examples I'm interested in, I believe would go under the family of Bars-Yankelvik theories. So you have 3 types of fermions. And so this is your gauge symmetry. And so you have fermions in the symmetric 2-tensor representation. Sorry, I'm going to use capital N. And I'm just going to assume that N is, well, I'm going to just take it to be 4n plus 2 for some little n. And then, so this has a gauge anomaly, so you have to cancel it by adding a bunch of other fermions. And then this is an SU n plus 4 symmetry, which also has an anomaly. So you can cancel that by adding some spectator fermions that are in the this representation. And then there's also a U1 symmetry. Good. So these symmetries are all non-anomalous, and there are other U1 symmetries. But what you can do is if you deform the theory by a 4 fermion interaction, which looks like psi, chi, psi, lambda, the proposal is that along some, if you add this operator to your theory, then these are the full set of symmetries. And the proposal is that when you flow to the IR, the theory confines, and you have an effective IR fermion, which I'm going to write as capital psi, which is the gauge invariant combination here. And then this interaction term becomes a mass term. And this gaps out the theory. Good. So a very mild thing you can do is you can double the number of fermions in your theory so that there's some additional SU2 symmetry, which I'm going to call SU2R. And so if you double, then these all transform in the 2-dimensional representation. And what you see is that actually SU2R also has none of the normal anomalies. It doesn't have any mixed anomaly with U1. It doesn't have a Witten anomaly. It doesn't have a new SU2 anomaly. But what you can show is that actually, in the case where capital N is 4n plus 2, there is, the anomaly erased. It does have this mixed anomaly between a 1-form symmetry and the fermion number. And the way to see it is you can see that if I wrote this in terms of, well, this transforms in the 2-tensor representation. This transforms under a 1 plus 1 tensor 1 representation, and this transforms under a 2 representation. So there's actually a common Z2 center here under which you can turn on a flux. And similarly, all of the fermions are in the 2, so that means there's a spin SU2 structure that allows you to go into a non-spin manifold. And then if you just compute the index, you find that it's non-zero. It's not 0 for this theory. And so what that means is that good. So if you can actually write down a similar interaction that preserves the SU2, and what you find is that, well, there's no unique choice of gauge invariant IR fermion because the 2 tensor 2 has 3 components. Oops, the 2 plus 2 plus 4, and so you could rule out the 4 because of that would have a new SU2 anomaly. You can't have both of these because it would have a Witten anomaly. So again, you can only have at most 1 IR fermion that transforms into the 2, which would flow to this. And so this term would again flow to a mass term that gaps out the theory. What I'm telling you is that there's this new anomaly that hasn't really been measured before or computed before that tells you that this can't happen. And so the suggestion is that, well, if this sort of mild doubling prevents you from gapping the theory, perhaps the original theory doesn't either. And I'm at negative time, so I'm going to stop here.
Regarding this last point, so is it possible that here is still gapped, but there is a TQFT in the infrared?
Yes, there is. This anomaly has. Oh yeah. So this anomaly implies 3 options for the infrared. Essentially, it's because this isn't really a one-form symmetry. Essentially the 3 options are it can be gapless. You can spontaneously break the symmetry. In this case, it'd be the one-form symmetry. Or you can have symmetry fractionalization for the spin SU4. Oh, sorry. Spin GF, which I guess in this theory would be the spin this SU2R. Yeah. So those are the 3 options, and you can prove that using topological field theory. Sergey, did you have a question as well? Okay, cool.